So let's step back for a moment and look at the way primary energy flows through the economic structure of a developed country. And we'll pick the United States as an example here. And on the left-hand side, we know that the input of primary energy is what sustains the economy. We also know that 80% of that input is from fossil fuel combustion currently. When we track this across the various sectors of the economy that consume energy, we always want to look at the electrical generation component, but we also have to sustain residential, commercial, industrial, and transportation sectors through a combination of energy from fossil fuels and energy input from electricity. But as we saw in the study of thermodynamics, the amount of energy rejected by this entire economic structure is 68% of the primary energy that goes into the left-hand side of this diagram. That is, we waste 70% of the primary energy. We only capture and use 30% of that primary energy. And we know exactly why that is. When we studied thermodynamics and we studied the Carnot cycle, we recognized that heat engines that take in heat, which we always write as Q in, produce work, which is work out, and dump the rest of that heat to the environment, which is Q out. We can calculate the efficiency of that heat engine cycle, and typically the efficiency for automobiles, for example, lies between 15 and 20%. That is, only 1 part in 5 of that chemical energy actually goes into useful work. And you can see that very clearly in the transportation sector. 20% of the primary energy that goes into transportation is actually useful energy. At the same time we studied heat engines, we studied heat pumps, and we recognized that a heat pump has this profound capability called the coefficient of performance, which typically equals just about 5 for modern systems. That means that when we're heating or cooling our house or our building, 1 kilowatt hour of electrical energy coming in produces 5 kilowatt hours of energy for either heating or cooling. We also finally recognize that while a gasoline automobile is 15% efficient, an electric automobile is 95% efficient in converting energy to motive force. So in the context of electrochemistry, let's dissect this flow from primary energy to its end uses in the current U.S. economy. And we remind ourselves that the total energy that is put into the system is just about equal to 100 quadrillion BTUs of energy. But if we look at how the primary energy flows, let's look first at the generation of electrical energy, because we see that coal is a dominant source of electrical energy. That is, the burning of coal in electrical plants that converts chemical energy to electrical energy. But we also see that a significant sector of this electricity generation comes from natural gas, which is methane. When we look at the natural gas consumption with respect to residential, commercial, and industrial endeavors, we see that natural gas is the dominant part of the energy input, and we see that petroleum is primarily directed toward transportation, that is, liquid fuels. But again, because we are losing some 65 to 70% of this primary energy as waste, we can ask the question, what happens when we use electrochemistry in this picture? That is, when we think about how residential, commercial, industrial, and transportation sectors operate, we recognize that electricity can drive all of those demands. It can drive heating and cooling, it can drive lighting, it can drive transportation for cars, trucks, trains, And we'll see the only transportation sector that electricity can't provide is that for aircraft flights, but we'll see a very tiny fraction of the total energy consumption goes to aircraft. And as we'll also see, biofuels are capable of covering that. So let's look at a world from the point of view of electrochemistry. So here we have a condition in which we are using renewable energy, that's solar, wind, geothermal, nuclear, and biofuels. And we notice that every single one of those renewable energy sources produces electricity directly. And that means that we can now use that renewable energy and directly put that into residential, commercial, industrial, and transportation sectors. But what's remarkable is that only about 10% of that energy is wasted in this process. That means that we move from some 100 quads of required primary energy in a fossil fuel driven system. We save a large factor, which means that we only need to provide 42 quads of total primary energy because of the efficiency of converting electricity into heating, cooling, lighting, and transportation. And that leaves just this one little thread from biomass for aircraft fuel. And because biomass is extracted from plants that have extracted CO2 from the atmosphere to provide the structure of their organic material, leaves, trunks, branches, and so on, that biomass is carbon neutral. So flying aircraft also becomes carbon neutral.